Hello. This is a Desmos calculator uh, demonstration of the underdamped oscillator. I've got two more later. So what I've done here is I've drawn the solution y1. It has value 1, derivative 0 at t equals 0. And y2 has value 0, slope 1. Now, I'm using the C1, C2 form of the solutions rather than the R delta because it's easier to satisfy initial conditions that way. But it has a slider here that will allow me to change the friction anywhere from undamped to almost critically damped, 0.999, so almost 1. So you notice that the period gets bigger as C increases. And then, of course, there's this envelope that decays quite quickly. Even though I didn't use the R delta form, I computed R for both of these solutions. So the R you see is actually 1 over 1 minus C square root of C squared. It's there. So this is the R e to the minus CT form. And by the way, I'm plotting all of these for omega naught equals 1. Okay, so yeah. So anyway, the high Q thing is just barely decays away. All right, now let's look at the next one, the overdamped case. I have the same Y1 and Y2 solutions. And one of the things you can see is that they both have this minus C plus square root thing. This is almost 0. This exponent times t. That's why you get the very slowly decaying part when c gets big. I should say this is almost 0 when c is large, right? And so even this solution down here, if you like hit it with a hammer, so it just comes up and then comes down, it still takes longer to come back towards 0 with a lot of damping than it would with a little bit of damping. So you can play with this if you want. And as I approach the critical damping, C equals 1, of course, if I put in C equals 1, I'd be dividing by 0 here, so I can't quite get there. But you notice that this is the case where the solution decays the quickest that it can. In fact, when you put a shock absorber on your car or truck, you want to choose the right shock absorber to get in a critically damped mass spring system, right? The springs are the springs. They call them springs in your car, and the mass is the car itself. And you notice if you put a lot of people in the car, that sort of also affects the oscillator. So I remember one time I have a memory of seeing about 6 people in a car next to me on the freeway, and they went over a bump and they started going up and down, and it took them a long time to steady down. They were definitely in an underdamped oscillation. Okay, so finally, let's see. Here we got the critical damping. So I've done a little bit a different thing here because I still have Y1 and Y2, but there's no C parameter to choose. So I went and I chose the C1 and the C2. So I can take a combination of those. So here's a combination of C1 is 1, C2 is minus 1. So in fact, I'm taking C1 minus C2 in black. And you notice if I do that subtraction, I'm just left with y is e to the minus t. So this black curve is just e to the minus t. In fact, this is the only solution, this or multiples of it, that never touch the t-axis, right? Most solutions touch the t-axis in one place, like here, or in general, right, this. Okay, let's get rid of these so we can see it. So, so one thing that's kind of fun, and maybe you might hear people say that if, well, here is an example of the oscillator is starts at y equals 1 and given a large negative velocity. So I hit it with a hammer down, and if I hit it hard enough, it will actually cross equilibrium and then slowly come back up, okay? But it's true that a lot of times, yeah, if I don't go down fast enough, it doesn't touch the t-axis at all for positive t. And that's what you hear sometimes. People say it never crosses the axis. In fact, all of these solutions cross the axis somewhere, except for that special one, the exponential. Uh, but it's just often at negative t, right? All right. So hope you enjoy these. You can follow the links and go right to these defined graphs. Okay. Goodbye.